Good afternoon, students. Boyle's law, Charles' law, ideal gas equation, and absolute zero temperature, and relationship between Kelvin, Celsius, and Fahrenheit scale. Now, the next topic is thermal expansion. Okay, almost all solids, gases, and liquids expand on heating and contract on cooling. Correct? When we will heat any object, it starts expanding, and when we are decreasing its temperature, it starts contracting. You have seen in the real life also that if you will heat up different metal objects or plastic objects, okay, they get expand. Correct? So this is the property of the property of the objects, that when we will heat them, they will expand, and when we will decrease their temperature or cool them, they will contract. Okay, so the change in temperature of body causes change in its dimension. When we will increase or decrease the temperature of any body, its dimension will be changed. Okay, so the increase in the dimension of a body due to increase in temperature is called the thermal expansion. Okay, when we will increase the temperature of any body, and then due to that the dimension of the body will increase, and that is called thermal expansion. Okay, now there are different types of thermal expansion: linear expansion, area expansion, which is also called superficial expansion, and the volume expansion, which is also called cubical expansion. Okay, so the first one is linear expansion. The expansion in length of a body due to increase in its temperature is called the linear expansion. Okay, when the length of a body is increased due to increase in its temperature, it is called the linear expansion. For example, this is the rod, it was having length L, then we have increased this temperature by delta T amount. Okay, that means we have increased its temperature from consider that previously its temperature was T2, and previously its temperature was T1, and then we have heated it up, so its temperature increases to T2. So the change in temperature or increase in the temperature is delta T. Due to increase in the temperature of this rod, the length of the rod increases by delta L amount. Okay, for example, if previously its length was L1, then we have heated it up, okay, and the temperature is changed by delta T amount. Due to that, its length also increases. Now the new length become L2. Okay, so L2 minus L1 is equals to delta L. This is the change in length of the rod. Okay, so due to increase in the temperature, the length of the rod has increased. Okay, so this delta L upon L is actually proportional to the change in the temperature. Okay, this delta L upon L is proportional to the change in the temperature. What was this delta L upon L? We have seen this previously also. This is like strain. Strain was same thing, na? Change in length upon original length. This is like strain. So delta L upon L, here it is proportional to delta T, that means change in temperature. Okay, so when we will remove the proportionality sign, there will be a constant, and here this constant is alpha. Okay, in subscript it is written L, so it is alpha L. That means the coefficient of linear expansion, that means when length is increased. Okay, so delta L upon L is equals to alpha L into delta T. So the alpha L will be equals to delta L upon L divided by delta T. or generally we can say that the coefficient of the linear expansion is equals to change in length, because it is delta L, so change in length divided by original length multiplied by change in temperature. Correct? This is the coefficient of linear expansion alpha L. Change in length, that is delta L, divided by original length, that is L, and multiplied by change in temperature, that is delta T. This will be the linear expansion, or we can say linear expansivity. It is denoted by alpha L. This was the linear expansion. The second one is area expansion. It is similar to that. The expansion in surface area. Okay, which area? Surface area. The expansion in surface area due to change in temperature is called the area expansion. Okay, when we will increase the temperature of a body, its surface area increases. Okay, then it is called the area expansion. Okay, consider this is a square of area. Okay, then we have heated it up and its temperature increased by delta T amount. Okay, so due to that the new area becomes this. Okay, so this area is increased by delta A amount. If the new area is A2, previous area is A1, then delta A is equals to A2 minus A1. This is the new area, and this is the change in area. Okay, again same, delta A upon A will be proportional to delta T, that is change in area upon original area is proportional to delta T. That means delta A upon A will be equals to alpha A times delta T. Here alpha A will be the coefficient of area expansion. Okay, so what will be the value of alpha A? Alpha A will be equals to delta A upon A delta T. Okay, so what will be the value of the coefficient expansion, coefficient of area expansion? This is given by change in area divided by, again, original area multiplied by change in temperature. Okay, this is the coefficient of area expansion or area expansivity. Okay, there is also relation that actually delta A upon A is equals to 2 times alpha L delta T. Okay, this alpha L is the coefficient of linear expansion. Okay, so that means actually the coefficient of area expansion is 2 times the coefficient of linear expansion. We will derive it further. Okay, there is an example in which we will derive this relation. Okay, so this was area expansion. The third one is the volume expansion. The expansion in volume of object due to increase in temperature is known as the volume expansion. Okay, if this is a cubical body, previously its volume was V, and then we have heated it up by delta T amount of temperature, then its volume increases by delta V amount. If the new volume is V2, original volume was V1, so delta V will be equals to V2 minus V1. Okay, here again delta V by V is proportional to delta T, so delta V by V is equals to alpha V times delta T, and again alpha V is the coefficient of volume expansion. So alpha V will be equals to delta V upon V delta T, again change in volume upon original volume multiplied by change in temperature. This is the coefficient of volume expansion, and here delta V upon V is equals to 3 times alpha L times delta T. Again alpha L is the coefficient of linear expansion. That means we can say that coefficient of volume expansion is equals to 3 times the coefficient of linear expansion. Okay, this relation we will also derive. Okay, these three were the types of the thermal expansion. First one was the linear, second one was the area or superficial, third one was the volume or cubical expansion. Okay. Now, now here it is a note. It is seen that the coefficient of volume expansion is not strictly a constant. Okay, here we have taken all these coefficient as the constants now, because there was a proportional reason, and when we will remove the proportionality sign, equals to will come and there will be a constant. Okay, that means alpha v should be the constant. Okay, but it is seen that alpha v is not strictly a constant. It becomes constant only at high temperatures. Okay, alpha v is only constant at high temperatures. For example, for copper, the coefficient of a volume expansion first increases with temperature and then it becomes constant at high temperatures above 500 Kelvin. Okay, and this is the graph of the variation of this. Okay, this was the temperature in the Kelvin, and this is the coefficient of volume expansion. E upon V, this is the change in volume upon original volume. That means no dimension will be here for the volume. So what is the value remaining? 1 by T, that is 1 upon Kelvin or per unit Kelvin. It is the unit of the coefficient of the volume expansion, linear expansion and area expansion, all of three. Okay, so this is the variation. First, as we are increasing the temperature, the value of the coefficient of volume expansion increases. It is not the it is not the linear relation. Okay, it is increasing. Okay, then it is increasing at the fast rate, and till 500 Kelvin the value is increasing, and after that it will become constant. Okay, so below the 500 Kelvin, the value of the coefficient of volume expansion is not constant. It will only be constant after the higher temperature, that is 500 Kelvin. Okay, so this was the volume expansion. Now, the another topic is anomalous expansion of water. Okay, anomalous means a different. Okay, water exhibits an anomalous behavior, that means different than others. What is this behavior? It contracts on heating between 0 degree Celsius and 44 degree Celsius. When we are heating the water between this temperature, na, it contracts. The volume of a given amount of water, as it is cooled from room temperature. For example, it is initially at the room temperature, and this is the curve for the water. Okay, initially the water is at room temperature, and now we are decreasing its temperature. On x-axis this is temperature, and on y-axis this is volume of 1 kg of water. Okay, so initially if it is at room temperature, and then we have started decreasing its temperature. Okay, as we are decreasing its temperature, its volume decreases till 4 degrees Celsius. Okay, so the volume of the given amount of water decreases as it is cooled from room temperature until its temperature reaches 4 degrees Celsius. Okay, so it will be cooled down until its value reaches the 4 degrees Celsius only. Below 4 degrees Celsius, now below 4 degrees Celsius, what will happen? If we will decrease the temperature further below 4 degrees Celsius, the volume increases. The volume increases, and therefore the density decreases. Sorry. Here, if the volume will increase, then density will decrease, na, because mass is equals to, sorry, density is equals to mass upon volume. Density is equals to mass upon volume. Okay, so mass is the constant, so if volume will increase, then density will decrease, na? So hmm. So below 4 degrees Celsius, actually the volume increases and therefore the density decreases. This means that water has the maximum density at 4 degrees Celsius. What is the maximum density of the water at 4 degrees Celsius? We know that. That is 1000 kg per meter cube. Okay. This is the maximum density of the water. We are using this value na always 1000 kg per meter cube because this is the maximum density of the water. Okay. This means that water has the maximum density at 4 degrees Celsius. This property has an important environmental effect. Bodies of water such as lakes and ponds freezes at the top first. Due to this phenomena, the lakes and ponds freezes at the top first. Okay. Why? As a lake cools towards 4 degrees Celsius, water near the surface loses energy to the temperature and becomes denser. Because density of the 4 degrees Celsius water will be more na than any other densities. So so the water become denser on the surface when it reaches the 4 degrees Celsius and sinks. So that water which is having the 4 degrees Celsius temperature, that will sinks because its density will be greater, and the warmer or less denser water near the bottom rises. Okay, the water which is below the surface will rises, and however once the colder water on the top reaches temperature below 4 degrees Celsius, if the water on the top surface reaches below the 4 degrees Celsius, it becomes less dense and remains at the surface because that density will be decreased na. What is the greatest density? The greatest density is at the 4 degrees Celsius, and that temperature, that water which is having the 4 degrees Celsius na, that will be under the under the free surface na, because at this point the density is greater, that is 1000. So if density is greater, that means it will remain below the other water molecules. Okay, so if this surface, this which is the free liquid surface, if this surface reaches the temperature below 4 degrees Celsius, then this will become less denser than the 1000 kg na. This density, for example, if this surface reaches the temperature, for example, if this is the free surface and this is the surface at 4 degrees Celsius. Okay. For example, if this surface reaches the temperature minus 2 degrees Celsius. Now, its density will be less than 1000 kg. Now, for example, its density will be considered is a 800, and this density will be 1000. Okay. That means this layer will remain above the 4 degrees Celsius temperature layer na, and this will freeze. Correct. This will get freeze because it is at minus 2 degrees Celsius and 0 degree is the freezing point. So the upper layer will freeze first. Okay, so lakes and ponds freeze at the top first. As a lake cools towards the 4 degrees Celsius, so water near the surface loses energy to the atmosphere and becomes denser and sinks. And the warmer, less denser water near the bottom rises. However, once the colder water on the top reaches temperature below 4 degrees Celsius, it becomes less dense and remains at the surface where it freezes. If water didn't have this property na, lakes and ponds would freeze from the bottom up. First they will freeze from the bottom and then they will freeze from the upside, so which would destroy much of their animal and plant life. Okay, so this behavior, this anomalous behavior of the water helps the water animals. Okay, now the next topic is relationship between coefficient of volume expansion and linear expansion. Okay, there is a simple relationship between the coefficient of volume expansion, that is alpha v, and the coefficient of linear expansion, that is alpha l. Imagine a cube of length L. Okay, for example, this is the cube and its length is L. Then its volume will be L cube. Its volume will be L cube, and if we have heated it up, its new length will be L plus delta L, and delta L is the change in length, and its new volume will be L plus delta L whole cube. Correct? This will be the new volume of the cube. Correct? So this was delta L. What is the value of delta L? We know that by the linear expansion. Imagine a cube of length L that expands equally in all direction, that is expanding equally in all direction. When its temperature increases by delta T, we have delta L is equals to alpha L into L times delta L T na, because alpha L was delta L upon L delta T. That means delta L will be equals to alpha L times L delta T. This is delta L, and delta V, here the delta V will be equals to what? Because new volume is L plus delta L whole cube and original volume was L cube. So this will be the delta V na, change in the volume. Change in the volume will be the new volume minus original volume. This will be the change in volume. And how we are getting this? See, L plus delta L whole cube. What is the formula for A plus B ka whole cube? It is A cube plus B cube plus 3A square B plus 3AB square na. So here it will be L cube plus delta L cube plus 3L square delta L plus 3L delta L square. Now L cube L cube sorry delta L cube and delta L square will be very less values. This is delta L na. Delta L means 0.001 something. That is it is initially very small. So if the delta L cube we will take, that will be very small, and delta L square will also be very small quantity. So we can neglect these values. Okay, so if delta L cube and delta L square will be neglected now, what will be the remaining value? L cube plus 3L square delta L. Correct? The remaining value for this will be L cube plus 3L square delta L. Now, in subtraction we have again L cube. So L cube minus L cube will be 0. So what will be the remaining value? 3L square delta L. This will be the remaining value. Only 3L square delta L will be the remaining value. This is the delta V. Okay, so delta V will be equals to 3L square delta L. Now in equation 11.7, terms in delta L square and delta L cube have been neglected since delta L is small compared to L. So now the delta V is equals to 3L square delta L na. Here delta V is equals to 3L square delta N. Can we multiply it by L and divide it by L? Then it will become, this value will become 3L cube delta L, and L cube is the original volume V na. V is equals to L cube. So it will become 3L cube delta L. So L cube will be equals to V, so it will become 3V delta L. And in denominator we will be having L. Correct? So delta V will become 3V delta L upon L, and delta L upon L is what? Delta L upon L is alpha L delta T, remember? So we will put this value here. So delta V will become 3V alpha L delta T. Okay. And we know that this is the delta V na. Delta V is equals to 3V alpha L delta T. and delta v upon v delta t is equals to 3 alpha L, and this value is equals to alpha v. That means alpha v will be equals to 3 times of alpha L. Okay, this shows that the coefficient of volume expansion is 3 times the coefficient of the linear expansion. Okay, now the next example, show that the coefficient of area expansion, that is delta A upon A delta T of a rectangular sheet of the solid, is twice its linear expansivity, that is alpha L. Consider this was the initial rectangular sheet okay, and its length was A and its breadth was B. Okay, then we have heated it up and its temperature increased by delta T amounts. Okay, so due to that both the directions will increase now. So A will increase by delta A amount and B will increase by delta B amount. So this will be the new shape of the body. Okay, this complete will be the new size. Okay, so we can divide this new points in 3 sections. This was the original area. Okay, now this is the new area. In this side is delta A, sorry, this size is not delta A, this size is B, this side is B, and this size is delta A. So this area is delta A times B, and we have considered is at delta A2. This is B times delta A. This area, this value was A, and this is the increase in breadth, that is delta B. That means this area delta A1 will be equals to A into delta B. And the last one, third area, this area in this side was delta A, change in length, and this side was also delta B, change in breadth. So area of this part A3, delta A3 will be delta A times delta B. This is the third area, third change in area. We have actually separated these areas so that we can do the calculations easy. So the total change area we can calculate delta A1 plus delta A2 plus delta A3. These all three are the total change in the area, correct? So these, consider a rectangular sheet of the solid material of length A and breadth B. When the temperature increases by delta T amount, A increases by delta A, and we know that delta A will be equals to alpha L A delta T, because alpha A upon A is equals to alpha L, sorry, delta A upon A is equals to alpha L delta T. So delta A will be equals to alpha L times A delta T, and also B increases by delta B amount, and delta B will be equals to again alpha L B times delta T. Alpha L is the coefficient of linear expansion now, and now we are consider the increase of one length. A length increased by delta A amount and B length increased by delta B amount. So we will use the coefficient of linear expansion only, that is alpha L. Okay, now because now we are considering the increase in one side, that is L or B. Okay, so we will use here alpha L, not the alpha A or alpha B. Okay, now the total change in area is delta A1 plus delta A2 plus delta A3, and we know all these values. Delta A1 was A delta B, delta A2 was B delta A, and delta A3 was delta A delta B. Okay, again, so delta A is also small and delta B is also small. So multiplication of these two we can be neglected. We can neglect here only directly. They have not neglected, but we can neglect it. Okay, because finally they are going to neglect this value. So this value will be neglected. Now A delta B. Delta B was alpha L B delta T, and plus B delta A. Delta A was alpha L A delta T. This value is neglected. because we have neglected delta A times delta B. Okay, only these two terms will be remaining. Now, what is common in these two terms? In these two terms, alpha 1 is common, AB is common, and delta T is also common. Okay, this term is not here, this is neglected, that's why this term is not here. Okay, that means all these terms will be common. So, what will be the remaining value? 1 plus 1. That means this will become 2 times AB alpha 1 delta T. Only this value will be remaining. These all terms will be neglected. So only these value will be neglected. Only the value remaining will be this 2 times alpha 1 A into B delta T. This value will be remaining. Okay, correct. Now what is AB? AB was the initial area na, that is A. Okay, so delta A becomes, now the delta A becomes 2 times alpha L A delta T. So alpha A upon A delta T will be equals to 2 times alpha L, and this value is equals to alpha A. Correct, this value is equals to alpha A. That means alpha A is equals to 2 times alpha L. This is the relationship between the area expansion and linear expansion. Okay, now there's a numerical question. A blacksmith fixes iron ring on the rim of the wooden wheel of a horse cart. Okay, the diameter of the rim and the iron ring are 5.243 meter. This is 5.243 meter and 5.231 meter respectively at 27 degrees Celsius. This was initial temperature. Okay, and these were the initial dimensions. These are the single dimensions, these are not the areas. Okay, respectively. To what temperature should the ring be heated so as to fit the rim of the wheel? Okay, we have to find the temperature till which the rim will fit the ring, sorry, wheel. Okay, here it is given the diameter of the rim was 5.243 meter and the iron ring was 5.231 meter. Okay, so we were given the initial temperature, that was T1, that is 27 degrees Celsius. Okay, and we were given these two values, the length of the temperature at 1 and the length at the temperature at the 2. That means what will be the length we want? We want the length, this length we want na, 5.243 meter, so that the rim will fit the wheel na. This length we want, this is the L2. Okay, we know that delta L was L2 minus L1 na, delta L was L2 minus L1. Now L2 we have, L1 we have. Okay, we have both these values. What was the formula? Alpha L was delta L upon L delta T, and we want to calculate the T2. We want to calculate the value of T2. Delta L we have. So what will be the value of delta T? Delta T will be equals to delta L upon L multiplied by alpha L. We can calculate from this term also. Okay, from that we have derived this formula. Length at temperature T2 is equals to length at temperature T1 multiplied by 1 plus alpha 1 T2 minus T1. Okay, put all the values here, we will get the value of T2. that will be equals to 218 degrees Celsius. Okay. The next topic is thermal stress and thermal strain. We will discuss this topic tomorrow in the class. Okay. For today it is enough. Okay. Thank you.